Okay, so we're going to look at different questions involving finding the area bounded by a curve and lines parallel to different axes. So let's look at this first question. So find the area bounded by the curve y equals 3 minus x times x plus 1 and the x-axis. So I want to figure out some things about my graph first. Okay, so um, just as a way to kind of help figure some stuff out. If I FOIL this out, I get 3x minus x squared plus 3 minus x. And so this would be the same thing as negative x squared plus 2x plus 3. So this gives me some important information. This tells me that I'm a parabola going upside down, which is helpful. I get my y-intercept, so I know that this is 3, and I know that my graph is going to look something like this. Okay. Well, I just need to figure out these 2 points, and I'm home free because I'm finding the area under this. So I go and if I look back at my original equation, now you could set this equal to 0 if you want, and that would give you your information. Or I could just use the factored form up here. Up here I can tell that one of my zeros is going to be 3. So that's here. So this is like x equals 3. And I know that my other one is going to be x is negative 1. So these are my bounds that I'm going to use. So imagine, for instance, that there are kind of imaginary line going up. Well, because I'm stopping there, because this is bounded by the x-axis, it's completely closed off. So I could go ahead and kind of set up my definite integral. So I'm going to integrate from negative 1 to 3 this function. And so this comes in handy now. Negative x squared plus 2x plus 3 dx. So that's going to equal negative x cubed over 3 plus x squared plus 3x. And I've got to do this from 3 to negative 1. So if I plug in 3, I'm going to get negative 27 over 3 plus 9 plus 9 by plugging in the 3. Okay, so each time. And then I'm going to subtract away, plugging in the negative 1. So I'm going to get negative 1 over 3 plus 1 minus 3. And so I need to go forward and simplify this answer the best I can. So this is negative 9 plus 9 makes a positive 9. And then this over here, got to figure out what that is. So that is 1/3 plus 1 minus 3. So that's 1/3 minus 2. And so that would be negative 5/3. And so overall, my total area is going to be 9 plus 5/3, which that should be 32/3. And you could find that extra answer in many different ways. But this is how you'd want to go about that. You need to find a picture. You need to know where your intercepts are, where at least it's bounded by. And then you perform the integration, the indefinite integration, and find the answer. Okay, so let's look at another question. So find the area of the region bounded by the curve y equals 4 over x squared, x equals 1, x equals 2, and y equals 4. So this one's a little different. So let's go ahead and draw out my map. So the equation y equals 4 over x squared. So that is a rational function. So it's kind of going to be something like this. Okay, and so I'm going to make this a little bit more pronounced. Okay, so I've got that. The line x equals 1. Well, if x equals 1, we'll say that's right here. Okay, that would mean that this point here, if I plugged 1 in, would actually be 4. So this is the point 1, 4. This is very helpful because that means that I know that this is the line y equals 4. So I've got that. I've got x equals 1. Got that. So I just need x equals 2. So I'll say x equals 2. So this is the area that I want. It's the one that's bounded by all of these things. That's what I'm looking for. So how do I go about this particular graph? This one being a little bit more difficult to find than maybe some of the others. So how this works is pretty easy. What we're going to have is we are going to look, for the difference in the areas of these two boxes. Okay, so look over here to the right. So imagine that we have this area and this area. Well, if we found the difference between the top and the bottom, it would just be that, which is what we're looking for. So in a sense, we are taking the area under y equals 4 and subtracting away the rest. So when we set up our definite integral, okay, so when we set this up, we're integrating from 1 to 2, okay, but we're integrating first, we're integrating 4, y equals 4, and then we're subtracting away the integral from 2 to 1 of 4 over x squared, which that's the same thing as putting them both together. So if you ever have to find the difference between two curves, you're always going to subtract away whatever the smaller one is. That's why if you look at the previous example, we didn't actually subtract anything away because we were using the line x equals 0. But if our line is anything different, we subtract away the one that is lower. So I'm going to go forward and perform this integration. So the integral of 4 is 4x. The integral of negative 4x to negative 2 should be a positive 4 over x. And I'm going to integrate that from 2 to 1. So I plug in 2 first, so I get 4 times 2 plus 4 over 2. And I'm going to subtract away 1, so 4 times 1 plus 4 over 1. This is going to give me 8 plus 2, so this is 10, minus, be 4 plus 4, which is 8. So my total area is 2 there. Okay, how about find the area bounded by the curve y equals 2 sine 2x plus cosine x and the xy axis. So let's look at this again. So this is a tricky one because you're dealing with a trig function, especially one that's got 2x. It's going to make this a lot easier if we can somehow convert this back to having the same angle measure as cosine. One thing I do know is that the sine of x, the sine of 2x, is the same thing as 2 cosine x sine x. So you could go and say y equals 4 cosine x sine x, and then bring that down, plus cosine x. So we need to know a little bit about this graph before we kind of go on. We need to know, because it's asking us about the area bounded by that and the xy axis. We need to know, like, what are our intercepts? Where do we start? Where do we finish? And so on and so forth. Where is its first intercept? So if we go and try to solve this, so we can factor out a cosine because they both have that. And you're going to get 4, you're going to get 4 sine of x plus 1. So your zeros are going to occur when cosine of x is 0, or when 4 sine of x plus 1 equals 0. So this is, let's see here, so we get okay, so x is going to be here. So this is first place is going to be pi over 2. And when is sine of x going to equal negative 1/4? So that's going to happen past that point. So this is going to happen later on, which we can actually kind of avoid that. So as we go along, our first zero, our first point, when we go back to our original, if we plugged in 0, you should get that we start off at 1. And then we crash down by another point. So it doesn't matter necessarily how it looks, but we know that it doesn't, it starts here and it crosses right there. So this is the area that we're trying to find. Now, this right here we found was pi over 2. So we've got all the information we need. Even though we don't know a whole lot about this graph, we know that it starts positive and it hits 0 at pi over 2. So we need to set up our definite integral. So we are going to integrate from 0 to pi over 2 the equation, and I'm going to use the original up here, make this easier for us. 2 sine of 2x, it was plus cosine of x dx. So that equals, so if I integrate this, you get negative cosine of 2x plus the sine of x. And we're integrating that from pi over 2 to 0. Okay, so we need to go ahead and plug these numbers in. And so if we plug in pi over 2, we get negative cosine. 2 times pi over 2 is going to be pi. And then we add the sine of pi over 2, which is 1. All right, so the cosine of, sine of pi over 2. And we're subtracting away, plugging in 0, which would be negative cosine of 0 plus the sine of 0. Well, this down here, the cosine of pi is negative 1, so negative negative 1 makes a positive 1. The sine of pi is 1. Then we have the cosine of 0 is negative, or is 1. So we get negative 1 here. And the sine of 0 is 0. So we get 2 plus 1 gives us 3. Okay, so find the area, bounded by the curve y squared equals 4x, the y-axis, y equals 1 and y equals 2. So this is a different kind of problem here. We're dealing with one bounded by the y-axis. So I want to kind of adjust this a little bit. I want this to be y squared over 4. Makes a little bit more sense for me. Or you can think about it as 1/4 y squared. So when we look at this graph, this is very much going to be very much just like a parabola. It's going to be very wide and facing the other direction. So we're looking at the y-axis. So we're looking at y equals 1. So this is y equals 1. And we're looking at y equals 4. And this area here. So we need to do things in terms of y. which is fairly simple for us since we've set ourselves up. So we're integrating the function in terms, we're measuring our lengths here in terms of x. Okay, so we need to you want your function with an x in one side. So we're kind of imagine like what we would normally do if we had y equals, but now it's just kind of in reverse. So we're integrating from 1 to 4. So we do from 1 to 4. And we're talking about the variable y, so we're using y's. And that is going to be 1/4 y squared by. So we want to go forward with this. So if we integrate this, we're going to end up with y cubed over 12. And that's going to integrate from 4 to 1. Now, I need some more space for this. So if we plug in that, you're going to get 4 cubed over 12 minus 1 cubed over 12. That equals 64 over 12 minus 1 over 12, which gives you 63 divided by 12 as your final answer. Okay, so lastly, it says find the area bounded by the curve y equals the natural log of 2x and x and the y-axis. Okay, so we need to figure out some things about the curve for the natural log of x. So the natural log of x and 2x kind of looks something like that. Oops. Looks something sort of like this. So what we need to do here is we are going to try and find some bounds. Okay, sorry. There was another condition on the problem which I knew there kind of had to be. We are only extending. We're only considering up until x equals 4. Which means that we have to figure out what this y line is going to be. We know that we're going to be using y equals 0 because we're integrating this way. And you may ask yourself why. Why couldn't we integrate like this? Why couldn't we do this a little bit more normally? Well, it's because this line doesn't exist before. Like the graph doesn't exist until a certain point. Until right here. So we have to, both graphs have to be present in where we're looking at the same time. So here, we're looking at the y-axis. You see we don't have to adjust the heights or adjust anything. Where if we went from here, right, this is kind of a different story. We're using the same set. So we need to figure out, first of all, what our y is going to be, and then kind of keep going on from there. So to find y, this one here, we would plug this in. So we're going to get y equals the natural log of 2 times 4, which is, this is the natural log of 8. So we get y equals the natural log of 8, which you may say, oh, yucky. Well, too bad. So we're finding this area here. So we need things in terms of x equals, not in terms of y equals. So we read this, so we have y equals the natural log of 2x. Well, we could reread this as the following. E to the y equals 2x. And therefore, x would equal e to the y over 2. And this is exactly what we want for this problem. So now we can actually go forward and find our areas here. Okay, so we're going to integrate to find our area. Remember, we're integrating from 0, which is here, to the natural log of 8. Okay, so integrating from 0 to the natural log of 8, and we are integrating e to the y over 2 dy. Now that equals, quite simply, e to the y over 2 from 0 to the natural log of 8. So we're going to plug these numbers in. So if we get e to the natural log of 8 over 2 minus e to the 0 over 2. Okay, so from here, then e to the natural log of 8, this is an interesting property of this because e and natural log are inverses of each other. The answer actually unlocks to be 8, so you get 8 halves minus e to the 0 is 1 over a half, and so you end up getting 7 halves as your total answer. So all of these things can be reduced. It makes a lot of sense to draw the pictures first, and then that way you can kind of understand which direction you're integrating and if your number makes sense or not.